So thanks everybody for coming, and thanks Tony for volunteering to give a talk in the computational biological learning group's reading group. I first communicated with Tony just over 25 years ago, which is a long time ago in my book. So I had started thinking about Gaussian processes at the time, and from the point of view of very large neural networks, which is arguably a quite tortuous way of thinking about Gaussian processes, but that was what we were doing at the time, and admittedly flailing around a little bit at the time, until one day I came across Tony's 78 paper on Gaussian processes, which was really a revelation for me. This was somebody from a different field who laid out beautifully and in a way that I immediately understood everything that was going on. So that was really a revelation that what we were trying to do, the underlying Gaussian process, actually really existed, because somebody had actually written something about it. And so this was a very happy day for me. So I wrote a euphorically enthusiastic email to Tony, which unfortunately I don't have a copy of anymore. And Tony was very nice, and he responded immediately. And I remember the last sentence of his email. He said something like, "So yes, I think that Gaussian processes are very interesting models, right?" And so I kept that little piece of advice. So anyway, we're here to listen to Tony and not to me. So I'm happy to pass over to Tony and hear about some of the Gaussian processes that he has known. Thanks, Tony.
Thanks very much. I'll just share the screen here, which hopefully will work. Oh, wrong one. Yeah, okay. Okay. So that's the title. It's really very much a personal thing, this. I'm not very good at knowing all the literature and all the references to what other people are doing. I tend to just plow along in my own way. And in fact, I write papers and wait for the referees to tell me who's done it before, which rarely happens, actually, quite nicely, because it seems that very rarely do people actually want to do things the way I do, at least at the time I'm doing them. So anyway, this is going to be a talk that's not very technical either. I've never thought it was great to put a lot of mathematics in talks. The very first talk I gave, even more than 25 years ago, was full of mathematics about these Gaussian process things, and I was really pleased with it. I thought it was excellent stuff, and then I realized that nobody was understanding anything beyond the first few lines. So all the mathematics is in the references. There'll be a whole pile of references at the end, which you can look up if you should want to. But hopefully I'll give you a taste of things, and maybe even enough of a taste for you to want to savor more in due course. So moving on. Okay, so why doesn't this move on? Ah, okay. So here's the outline. Gaussian processes, the way I use them in statistics and the way as I understand it, they tend to be used in machine learning. Then I'll talk about regression, the original paper that was the 78 paper, and some other related examples. And then I'll move on to the major subject of the talk, which is uncertainty quantification in computer models. So, first of all, I'm sure you know a Gaussian process is a probability distribution for an unknown function. At any input, f of x is normal, mean mx, variance vxx, and at any finite set of points, the joint distribution of the value of the function at those points is a multivariate normal with a covariance matrix made up from that covariance function. So it is effectively an infinite dimensional multivariate normal distribution. It is the unique extension to that uncountably infinite space of x values of the specification just above of multivariate normal at any set of points. So it's defined by giving it a mean function and a covariance function, and the main issues around developing Gaussian process applications are all around how you define those things best to match the application that you're working on. There are other challenges associated with computational and solution to problems, but the main modeling skill is kind of always important in there. Typically, there are hyperparameters in these functions. So you define your mean function, your covariance function, as involving other parameters that you don't know, which need to be estimated as you go along. So I've used Gaussian processes after that initial use for various problems in statistics, but I, of course, didn't invent these things, and I didn't develop them from scratch. It was presented to me just in the same way, a revelation to me when I was shown what the Gaussian process could do. But at that stage, I guess it hadn't been propagated out into the mainstream statistics. It was around sort of in the forecasting world. Anyway, Gaussian processes are also widely used in machine learning, but I think there are some important differences as I perceive them, unless of course you've moved on such a lot that you're doing things differently from how I think. So I generally use the formulations like this. I write the mean function in a regression form. So there's a set of known functions h of x, that's a vector, and a vector of parameters beta that is there are hyperparameters we don't know. Then I always use covariance function, which is a Gaussian kernel, has an unknown parameter sigma squared, and in principle an unknown matrix D. Remember, x itself can be a multivariate, so we can be operating these functions in many dimensions of x space. Okay, so the reason I use the Gaussian covariance function is the applications I've tended to work with are ones in which we know that the function f is smooth. It's analytic. It has as many derivatives as you want it to. That may not always be the case, and there are obviously other covariance kernels you can use, and I'm well aware that in machine learning, quite often those other kernels are in use. But as I understand it, machine learning, you typically use a zero mean process, but in effect, you put that regression function into the covariance term, which is fine. I seem to have missed a beta out of the expression there for the hx transpose should be beta transpose v beta, maybe beta v trans beta, oh, whatever. Anyway, it should all be there. There should be another beta. Okay, so that's how I think there are differences. And there are also differences in terms of the sort of things we're trying to do. In the statistical problems I deal with, typically we have rather little data. So it can be of a wide variety of types, but we're trying to use the Gaussian process in a context where we actually don't have masses of data to fit that Gaussian process to. And we tend to be concerned to get the best analysis of the case at hand, particularly in Bayesian applications. So we're doing a proper Bayesian thing. We're using proper prior beliefs about things. Now, as I understand it, typically machine learning doesn't do all of that. You often have large quantities of data. You are concerned about routine automated analysis. I tend not to be doing that. I tend to be dealing with things that are specific to a particular problem. Your observations always have error. I may be mistaken there, but I've done applications in which they don't. So let's move on. So yes, in 1977, I discovered Gaussian processes. Well, I was introduced to them by Professor Jeff Harrison, who was the professor at Warwick University in statistics when I was there. And paper appeared in 78. In which they used. Problem I was trying to solve was a problem I brought to my early days, having had experience in real-world applications of statistics where people were designing experiments and fitting regression models to those experiments. So there was a theory of optimal design of experiments, but this theory always said you had to work in a limited X space to optimize in, because if you broaden the X space out, you would keep pushing observations out to the limits. And the real world isn't like that. The real world doesn't have models that behave nicely all the way up to infinity. So you tend to be interested in fitting over a reasonable space, but not being able to confine that restrictively. So that was what I was trying to do, was to solve the problem of design of experiments in regression. The observations are of this form in the model I used. Y is h of x transpose b of x plus error. But the usual regression model has b fixed. I'm going to allow that b to vary over the x space. So my coefficients of the regression model vary. So it's not going to be a nicely behaved, say, quadratic. It may distort as we move away from the area we're particularly interested in. And that's what's going to cause you not to want to push observations out to infinity. Because when you do so, B has transformed so much that it's not useful to you in the area you want to predict in. So I use a Gaussian process prior distribution here for the parameters of that model. And then I also showed the more general case where we just have a general non-parametric regression, and mu itself has a Gaussian process. It's observed with error, and the posterior mean is going to smooth through those data points, allowing for the fact that they don't equal mu, they're observations of mu. And it's a classical use of Gaussian processes subsequently in machine learning and in various other places. I didn't write the paper to do that. I was trying to do this fancy spatially varying coefficient model. Nobody ever looks at that again. They only ever cite this paper because of the use of the general Gaussian process in there. So, and nobody's ever used it really since for the original purpose. A shame, but there you go. It was very complicated. But then Gaussian processes have sort of gradually taken off. It took a long time for there to be many citations of that paper, but over time they grew and grew and grew. And now they've become, as I say, almost ubiquitous tools in various fields, which is nice, because it means I've had loads of citations of that paper, even though probably people mostly never read it. But I'll concentrate on the applications I've been involved with. So I'm going to give you two brief examples at the start to show you just the diversity of applications that you can have. And these are cases where there are observations made with error. And then I'll move on to another area that's become a big research field, which is called uncertainty quantification in computer models. And I'll throw in a little aside on expert judgment in there. So this radiocarbon dating application, archaeologists date objects using radioactive decay of carbon-14. So all living creatures absorb some carbon, have built up very largely of carbon, but they absorb some of this carbon-14. It's an isotope, it's not a radioactive isotope, but it's an isotope of carbon, which is created in the atmosphere by solar radiation acting on the carbon dioxide in the atmosphere, and you get carbon-14 created. And then it's absorbed and goes right around the biosphere. But as soon as an animal dies, it stops taking in carbon-14, and the carbon-14 that's in it gradually decays back to carbon-12, which is the neutral version. So the technique is to count how much carbon-14 there is relative to all the other carbon in a sample of a dead thing that has been alive. And if as that proportion of radiocarbon, carbon-14 decays, then you get a measure of how old it is from that, because you know how fast this stuff decays. So if the level of carbon-14 in the biosphere were constant, and all creatures when they were alive had the same proportion of their carbon being carbon-14, then you just get the age of this object, Y, is its radiocarbon age, X. But unfortunately, that's not true. We know that there are times when there's more carbon-14 around and times when there's less. So there's an actual calibration curve, f of x, that relates carbon age to real age. And it's not even a monotonic function. We have data from various kinds of dating, other kinds of dating, for everything except a long time back. It's tree ring dating, what they used to identify ages of things. So you count the number of tree rings, then you take a sample of the tree at that ring, and you radiocarbon date it. So we treat the radiocarbon dating calibration curve as a Gaussian process. It's like the non-parametric regression, except we're going to have different modeling of prior beliefs about that curve related to knowledge about the processes that generate carbon-14. So we know that this is a smooth varying process. And this is a sample, a portion of the radiocarbon calibration curve. You can see it does wiggle. And the people that were working on this had a technique called wiggle matching to try and match up a tree. So if you've got a portion of tree that is already dead, you don't know when it was felled, but you can look at the widths of the tree rings and try and match those to the pattern of widths of tree rings in samples that are overlapping with it. Anyway, that's dendrochronology. But here's a portion of the calibration curve. So you can see the measured values plus and minus, because obviously the radiocarbon dating is not perfect. Depends on how large a sample you've got to date it with. And that was that application. And there'll be references at the end of the talk if anyone wants them. The other quick one is the spatial interpolation. So monitoring stations measure atmospheric pollutions at various sites. We want to estimate pollution at other sites by interpolating between these sites that are called gauged sites. So we observe them at the gauged sites, want to interpolate that function. Now, standard geostatistical methods will do that. They're called Kriging and so on. They're all equivalent to having a Gaussian process prior. But those methods typically rely on you being able to say the process is stationary and isotropic. So effectively, you're going to use a stationary mean function, you're going to use an isotropic covariance function in your Gaussian process. But we know that's not appropriate in this case, because we know that the geography of the site is going to affect where the pollutants pool up and where they don't. So we need to allow for that. So what happens is that a paper by Sampson and Guttorp way back, they developed an approach in which they map the location, the geographical locations, what they call G space, into a latent space called D space. And then the correlation function is a function not of distance in G space, but of distance in D space. So it's an isotropic, homogeneous Gaussian process in D space. And then they need to estimate the locations in D space for a given geographical location. They do that by classical statistical techniques, multidimensional scaling, and in thin plate spline interpolations. I produced with a research student a Bayesian approach using a Gaussian process prior. So we don't have those arbitrary choices. But this also is another technique that was fancy and nice and publishable, but nobody's used very much, because actually fitting this Gaussian process to this thing is hard. It's kind of deep buried. It's not, you're not observing the Gaussian process but with error. You're observing the geographical process with error, and then underneath that you've got to model this mapping. So those are two quick applications just to illustrate the variety of areas where these things get used. Let's move on to the main subject, the uncertainty quantification for computer models. So this begins with the second time I used Gaussian processes, and this was for numerical integration. And I called it Bayesian quadrature or Bayes-Hamid quadrature because we used a Gaussian kernel. The problem is to estimate the integral of a function over some range. So we observe the function at some points. We compute the function at some points. We then treat that function as an unknown function, put a Gaussian process prior on it. It's observed now without error. And so the mean function of that Gaussian process is going to interpolate the data. At those data points, the Gaussian process mean will pass straight through the points, and the variance will go to zero because we know the value of the function at those points. So then we just can analytically derive the posterior distribution of the integral from that. And that's around this kind of modeling, not necessarily just this, and I wasn't the first one doing all of these things, but this field of probabilistic numerics has grown up around this kind of modeling, and I get cited and have been invited to give talks to these people when I've got nothing new to tell them in their field. I guess I've got nothing new to tell you either, but it may be something you haven't seen before. So that Gaussian quadrature theory was a natural answer to another problem. I had a guy came to me, he wanted to do a PhD, and he was going to quit his job, which was with the National Radiological Protection Board, and do a PhD. And I said, well, what sort of things are you doing there? And it turns out what he was doing was something that we could really apply this Gaussian integration process to, this Gaussian process integration, and get answers to questions that actually mattered in his job. So he didn't quit his job. His employers kept him on and gave him lots of time to work on this thing. So we have a computer model we call a simulator. It produces an output when given inputs. Okay, so X is typically a vector. Y can be a vector, but usually we illustrate things with one-dimensional things. In his case, the computer model was modeling how radionuclides are passed around your body once you've ingested them and where they settle in your body. So the output Y would be the concentration of radiation that you've absorbed in, say, the thyroid, which is where you pick up the iodine radiation. So the inputs X are uncertain parameters in this model, typically. Parameters of transfer between different compartments in the compartmental model. But for any particular application, we don't know those X's. So X is a random variable, and therefore the output Y is a random variable as well. It's a function of a random variable. And we're interested in the distribution of Y, call it the uncertainty distribution. And in particular, if you want to estimate Y, you want the expectation of that distribution. Well, that's just an integral of this function X with respect to the distribution of X, expectation of f of X. So we can just use the Gaussian process stuff. Now, what they were doing in principle was Monte Carlo. You sample values of X from its distribution, you run the model, and you get lots of values of Y. Brilliant idea in principle. Problem is, it's not practical if the model takes a long time. So some of these models might take hours, or even some of the applications that take days to get one single run, one single value of Y. So we can only do a small number of runs. And Monte Carlo, brilliant if you can do thousands and thousands of runs, preferably millions, but not if you can only do a handful. So the Gaussian process solution, treat this as an unknown function with a Gaussian process prior distribution, training set of runs, observations again without error, derive the posterior distribution, make inference about the distribution, and in particular, you could make inference about the mean, the variance, and so on. They're all integrals. Equally, the distribution function of Y is an integral, and so on. So all of that comes straight out of that Bayesian quadrature theory. Now, the engineering and applied maths community called this uncertainty quantification. Much later, I mean, it's a relatively recent term. It's a terrible term because it implies that they're going to do much more than they do, and it implies that they've taken over the whole field of statistics. Statistics is exactly about uncertainty quantification. So anyway, but that term has stuck because there are a much, much bigger community than statisticians. So there's tens of them for every one statistician. So we can't win that fight, and we lose out to you guys as well, who keep inventing names for statistical terms that we already had. But anyway, moving on. The basic idea, you use a training set of runs to build a fast approximation of the simulator. And they call this a surrogate model. And then you propagate uncertainty in X through the surrogates to approximate the uncertainty distribution of Y. And you can do various other things with this, but the basic idea of uncertainty quantification, UQ as they call it, is propagating uncertainty through a model by means of developing some kind of surrogate. And the Gaussian process mean function is a popular surrogate. It's an obviously good surrogate. It is an approximation to the whole function, which agrees with the runs you've made. And with a relatively small number of observations or actual runs of this model, even in large input space X, you can approximate that simulator output reasonably quite accurately using the Gaussian process. But there's much more uncertainty than is normally acknowledged by the UQ world. So first of all, code uncertainty, as I call it, that's uncertainty in the fact that you've used a surrogate. So your surrogate produces an approximation to the function. What about the uncertainty around that approximation? How good is that approximation? Next is model uncertainty. So the simulator is never perfect. It can't be. Simulator itself is an approximation to the real world. How do we quantify that uncertainty, that possible error in the predictions we're making? And then another one is that in UQ, they always assume you've got the distribution for X. It's been given to you. But where does it come from? In practice, there will be uncertainty about what the distribution of X is, and we ought to include that as well. So several kinds of uncertainty that they don't acknowledge. So the code uncertainty is a doddle for the Gaussian process. We've just covered automatically. We have the full probability distribution for the function. It's the Gaussian process. It's much more than a surrogate. I call it an emulator. A surrogate just gives you this estimate or approximation. If you've got an emulator, you have a proper expression of uncertainty around the estimate. Any surrogate that also has a credible expression of uncertainty can be an emulator. It's just that I don't know of any others, because one thing that the Gaussian process does is it knows that it's got true values at the observed data points. So when it does that, it's got the mean passes through those points. So this is a surrogate that is an interpolator. It's not a smoother. And also, the uncertainty goes to zero at those points. I don't know any other standard technique in UQ that gives a surrogate that does that. So there are no other things that I would call an emulator. The next thing, all models are wrong. Even when you give the model the true optimal inputs, which you don't necessarily know the values of, but even if you were able to know the true values of the inputs, f of x would not equal reality. The difference we call model discrepancy or model error. When I first introduced the term, I called it model discrepancy so as not to upset the modelers. I wasn't going to call it model error because that would be kind of a criticism of them. Whereas we know that no models can be perfect. So there's always a discrepancy between the simulator and reality. And we can hope to learn about that if we observe reality, although we can't observe reality without error. There will always be observation error in reality. So how are we going to model all of this? Well, first of all, we need to distinguish between two kinds of inputs. There are parameters. These are inputs that are fixed, but have uncertain values, like in the nuclear medicine problem. There was unknown parameters that describe the way that the radionuclides move around the body, the transition rates between different compartments of the model. Those are parameters. They're inputs to the model. You have to give them numbers to run the model, but you don't actually know what those numbers are. Control inputs are inputs that you give to the model to tell it what prediction you want from it, where and when and so on. So for instance, a simulator predicting deposition of radionuclides after a radioactive accident, so a Chernobyl type accident, stuff is spewed out into the air, blown around, where does it end up being deposited? The control inputs here will specify, certainly they'll specify location where you want to know the deposition. The parameters will include all those unknown things like the amount that was released, the wind direction, wind speed, and so on. When we're modeling the model discrepancy, we have to distinguish between these two things. So we have training data, which is straightforward. We actually run the simulator, observe values of the simulator. In the jth training run, we give it control input values and we give it parameter values. And we specify these, we choose where they are. We choose a set of those different values of x and t so as to spread around the space in order to be able to fit the simulator to the Gaussian process and get a good representation of the simulator. But we also have these real world observations. So Zi, the ith observation, is the simulator value at the appropriate control input, which we know, psi, but also at the vector of true values that we don't know. We need to introduce the control inputs here because when we observe the reality, we observe it at several different points. So we have different control input values for those observations. Model discrepancy is a function only of the location or whatever, the control inputs. Okay, and then we have observation error. So we need to be able to estimate this model discrepancy function from this model. So using the training data and the real world observations, oh, did I say that's another Gaussian process, of course, the model discrepancy function. So we've got two Gaussian processes here, F and delta. Using both sets of observations, we can make inference about the simulator. That's just the emulation. That's only actually using the training data. Although actually, when you put in the real world observations, you do add knowledge about the simulator if you've got different control input values for the real world observations, even though it's observed with much more uncertainty. You can learn about the model discrepancy. You can learn about the parameters. This is called calibrating the model. We can learn about the hyperparameters of the Gaussian process, of course, and we can learn about reality. So our predictions of reality from this model are calibrated. We've learned about the parameters, and their discrepancy corrected because we've learned about delta. So in principle, we can actually make credible, realistic predictions of the whole of the reality we're interested in, and not just what the simulator thinks the reality is. But there's a substantial requirement of resource in here. Fair enough, getting more training runs is often more expensive. So that's a lot of computing involved in that. It can typically be small compared to the computation required in doing this. But real world observations can be even more expensive to get. And typically we have very few of those. So how do we validate and criticize this kind of modeling? Well, to validate the emulator, we make additional simulator runs, compare them with the emulator predictions. And there's various tools and tests developed. And that's relatively straightforward. We should always do it because we can always make a few, at least, extra simulator runs. I've put at the bottom there, expect failure. No model is perfect. The Gaussian process makes assumptions about the way this thing operates, and they may not be right. The real thing we're trying to emulate, the real function, the simulator, may not be as homogeneous, as nicely behaved, as smooth as we think it is. So it's typically the case that when you do this testing, it doesn't fit perfectly. You add in the new runs, you get a better emulator rather. It probably still isn't perfect. It probably still doesn't perfectly represent the uncertainty, the code uncertainty component. So even when we've claimed to incorporate all of these things, there's modeling goes on in order to do that. Nothing is ever perfect, but we're a whole lot more perfect than the UQ people would typically be. When it comes to validating the model discrepancy, that's even harder. You can make additional real-world observation in principle, but typically you've got a very poor estimation of this whole thing anyway. And furthermore, an important feature, and something that I failed to recognize when this paper was originally published, it was a discussion paper for the Royal Statistical Society. And it was pointed out to me in the discussion that I failed to acknowledge it, that there is a non-identifiability here. You can't separately identify the model discrepancy and the parameters from the data we've got. So they are inextricably linked. You can predict reality. You can't ever learn perfectly what the discrepancy is or what the parameters are. They depend on each other, and the combination of them is observable, is known if you get enough data, but you can't actually separate them out. And that's kind of important to know. But anyway, we can do some testing of this process, but at the end of the day, only very limited, and you do the best you can. This process is now very widely used, and the paper that introduced this model discrepancy thing has even more citations, huge number of citations, again, from people who probably have never read it. So the third area of uncertainty that is not accounted for by the UQ people, and indeed is not routinely accounted for in any applications I'm aware of, is the fact that you've got uncertainty about the input distributions. So first of all, where do they come from? Well, they're kind of judgments that people make usually. There's not usually a mass of data to draw upon. And this whole judgment area is something that I've worked in a lot myself. And in fact, is the thing I spend most of my time on these days, is eliciting expert judgments, expert knowledge about uncertain quantities, typically to be fed into models. So deriving these input distributions is a major area of my own research these days. It's called elicitation. Typically, you require a group of experts because you don't want to just use the judgment of one. You want to get a broad spectrum of input. The way I do it, we talk through the evidence with the experts and they debate. And at the end of it, they reach a kind of consensus distribution. Now, it's important to understand what this consensus is, and it needs to be explained to the experts themselves, because they all will come in with different opinions about the thing you're trying to elicit judgments about, and they will all go out with different opinions. Their opinions might have changed a bit through the discussion and the sharing of information. They may have converged a bit, but you won't end up with them all believing the same thing. So the kind of consensus we ask them to reach is to imagine there's somebody been observing all of this. We call them the rational impartial observer, RIO. And this person, it's their opinions we want to get. Now, of course, that person isn't there, but what do these experts think a rational impartial observer would reasonably believe based on the evidence, the opinions these experts have expressed, and the discussion they've had? And that turns out to be feasible. They can actually think about that, make those kind of compromises, and reach a consensus distribution, which is the kind we want. It sort of represents what a knowledgeable person in the field ought to believe based on what's available in terms of evidence and opinions that are out there. And indeed, typically we're doing this for a client who wants the distribution to input it to a model, to make decisions. And the client wants this overview opinion of what the community at large might think. So that kind of consensus is something we do. And this is the process that I use. It's called SHELF, the Sheffield Elicitation Framework. And other people who do elicitation do things somewhat differently. So they don't seek consensus like this. They typically don't have experts brought together to talk. They ask them separately what their opinions are, and they apply an algorithm to combine them. Something which might actually appeal to machine learning people who love algorithms and objective processes. This isn't the way we do it. SHELF is, if you like, a subjective process. A lot depends upon how you manage the discussion. You need good facilitation skills. But that's something that I spend a lot of time these days teaching. So I've been training up other people, and particularly some companies who want to use this routinely. I train up facilitators in the company to use the SHELF process. Okay, so far so good. Where's the Gaussian process? Well, this whole process can't be exact. The judgments the experts make are fallible. They would make different judgments on a different day, a different group, would that interact differently? They'd come up with different answers. There is uncertainty and imprecision in what we get. So in Shelf, the experts provide a small number of probability judgments, typically 3 or 4 probability judgments, consensus judgments at the end. Probabilities that the uncertain quantity X is less than some C value. They specify a probability. Should be an FC. So F of C. So 3 or 4 different values of C, they give the probability that X is less than C. And then we fit a suitable probability distribution to that, normal or beta or something. But there is arbitrariness in this fitted distribution, and there was imprecision in the original judgments. Nobody judges these probabilities to 3 decimal places. You know, it's all approximate. So here's where the other Gaussian process comes. We assume that the experts, or their judgment of what Rio's probability distribution would be, is an unknown function. It's an unknown density function. We specify a Gaussian process prior distribution for that. It will be generally uninformative, but what we actually do is we say that the expert's density is an underlying Gaussian or something else modified by a Gaussian process. So you take the Gaussian, the normal distribution as the mean function of your Gaussian process, and then you apply the uncertainty around that. And that mean function, of course, has parameters in it, which are the hyperparameters of that probability distribution that you're taking as your model. Okay, and then the expert judgments are data, and the posterior Gaussian process will then estimate the expert's density in a way that agrees with statements they've made. What we're observing here is integrals of the Gaussian process. So it's a different kind of observation here, but integrals of a Gaussian process are Gaussian processes. So we're observing that with error, because typically we must allow for the experts being imprecise. So where in the typical elicitation we fit a distribution, we might fit a normal distribution or a gamma or a beta distribution. In this process, in this approach, you take that distribution to be the underlying expectation of your Gaussian process, the underlying mean function, but you allow variation around that. And then you also allow for the experts not to have judged their integrals exactly. So here's an example that the histogram represents the stated probabilities that they've given. In this case, they've given quite a few, 6 different probabilities, which come together to make that histogram. On the left-hand side is the distribution that the Gaussian process fits after you've given those probabilities without allowing for any error or imprecision in the expert's judgments. It's taking those probabilities, that histogram, as exact. So the Gaussian process fits through there in such a way that all those blocks, the areas under all those blocks, equal the area under the curve in the relative area. So you can see that from those probabilities, there's very little uncertainty as to what is the underlying density, but it's not a normal or a beta or a Gaussian or whatever. It's got bimodality in it, and that's from those experts' judgments. Now, if you showed the experts that, they'll probably say, oh, no, that's not really what I believe. And in a regular process of doing the elicitation, we would go through and do various other adjustments, ask them if they want to vary their probabilities. There's always a lot of checking goes on of their judgments, and if necessary, we vary them to get some sort of better representation. If they indeed looked at that histogram, they'd probably think it was a bit strange. So then if we allow for uncertainty in their judgments, you get the right-hand picture. Now we can see that a relatively nice, smooth distribution can fit through there. It's got more uncertainty. The 95% bounds point-wise are wider, but it's still a reasonable representation of what they've done. We're saying that their judgments of those high, narrow probabilities, they're probably a bit too high. And in particular, they're a bit underestimating the right-hand side probabilities. You show them this, excuse me, and they're as long as they see it fitting reasonably well to their beliefs, they're much happier with a distribution like the right-hand one than the left-hand one, generally. You don't have bimodality in people's judgments unless there's a good reason for it. So that's another Gaussian process. This is published. It's, again, another one that people don't use. And even I don't use it, even though I do all this elicitation. And with my colleague, Jeremy Oakley, who worked on this and who does a lot of this shelf stuff, the elicitation stuff with me, we have as a plan sometime to implement it in our routine shelf package. It just hasn't been done yet. So there's lots of nice Gaussian process applications. I'm sure you have the same experience. You have lots of these nice applications, most of which never get used, but one or two are picked up on and are widely applied. So that's the end of my talk. There's lots of papers in the bibliography, more than you probably ever want to look at, but you can pick out some of those topics. If there's anything you're interested in, you can read all the gory details. And that's it for now. Thank you.
Great, thank you very much for your talk, Professor. Perhaps the best thing to do now is to move on to discussion. Given that there's over 80 of us here, can I ask that if people want to ask a question, they use the raise hand function, and then I can just call your name? Or type it in the chat, that's another option. We got the first question here from Adria.
Wow. Thank you for the talk, Professor Hagen. It was very interesting. A couple of things jumped up to me, but maybe the thing I want to ask is a bit dramatic. What are that in machine learning we've reinvented many terms from statistics and called them different names, and it seems like we could benefit from knowing what the original names are and reading what people have written about that. So what are some of the terms that you think machine learning has reinvented and done in a poor way?
Oh, gosh. No, that's a good question. I sort of throw that out because it's something that I believe, and I certainly, if you'd asked me this 10 or 20 years ago, I would have said, oh yes, this, and this. So, I mean, neural networks, for instance, they're just a certain kind of generalized linear model type idea. So, you know, okay, it's a nice name, but even machine learning and just terms like that, artificial intelligence before it, we just felt that statisticians felt that you guys were sort of charging into our territory, reinventing things, and if you'd only listened to them, we could have told you why they worked in the first place. You see, you're again, I'm going to be very controversial here. You're working in a field which is incredibly Darwinian. Okay, there's thousands of you dreaming up new things all the time and trying to get other people to pay attention, and it's all very fast. You go to all your conferences and you present papers at the conferences or posters and things, and they don't ever, well, they don't need to get published because people are rapidly jumping on them. So you've got this fast turnaround of papers and so on. And what happens is that if nobody knows why some of these things work better than others, but the ones that do are picked up, and mostly people find that they work better and they're taken forward. And it can be that a statistician comes along later and tells you why that actually works, or doesn't tell you because you're not listening, but that's my impression I have. So it's a survival of the fittest of all your ideas out there, which are, you know, thousands of them thrown out at every conference you go to. Am I totally unfair?
No, I think this is very fair, and the field actually has been pushing a bit against this. It's usually called grad student dissent. Yeah, and so there's definitely a push to make people explain their hypothesis more, or like test the hypothesis about why something works, as opposed to just throwing it out. But okay, yeah, this seems fair.
We all do it, of course. We all do it. I mean, I throw out ideas that I think. I mean, the whole elicitation thing. You can't test whether many of the techniques you're using work, because you can't do serious elicitation with serious experts on serious problems and replicate. You just can't do it. So a lot of it is, I think this works, and people follow that, or they follow somebody else who thinks something else works.
Maybe at longer timescales, this will be Darwinianly selected in or out. But yeah, I'll leave it be. Thank you very much.
Thank you.
Great. I think Carl wanted to say something.
Oh yeah, so I have another question about the relationship between statistics and machine learning. Or so I think, as you alluded to already, machine learners, they have this sort of obsession that they want to turn things into an algorithm, right? So they want to sort of automate things, and whereas statisticians, they're sort of happy to sit down and think about an individual case and kind of try to do the best they can in the individual case. And I, as a machine learner, or more of a machine learner, I sort of think, I only really think I understand what's going on if I can formalize it enough that I can write down an automated procedure, right? Then I think I know what's going on. So do you have an attitude towards, are those two approaches, are they complementary? Are they going to merge, or is it just a different way of thinking about science or understanding numbers? Do you have an attitude to that?
Yeah, so it's interesting. As a Bayesian statistician, I'm always interested in as a real hard-line Bayesian statistician, probably. I'm always interested in the real prior information and exactly what is known in a particular application. I tend to gravitate into areas where there is actual meaningful prior information that I can code up in some way, because that's where I think that the skills of the Bayesian statistician, the Bayesian modeler, are best used. But when you go and publish the things, you will typically present a generic version of what you've done for the benefit of other people who can follow on in doing that. So both things are happening anyway. So and we also have this Darwinian sort of thing as well, because frequentist statisticians don't have to have any basis of actual knowledge under there. So our journals are also quite full of speculative, here's another way of doing this kind of thing, whereas the Bayesian actually goes in and says, what's the right way of doing this? Because once you tell me what the knowledge is, I know how to model that and give you the solution. So all of these things are there, and one reason why you don't see quite so much Bayesian stuff actually in the journals is because we do applications and not always come up with the sort of the general thing. And I'm at fault on this. There are a number of things that I've put into my own work just for the particular case I was dealing with, and not realized that here's a tool that could be more widely used. So all sorts of things that went on. So way back, one of the first things I did as a graduate student was trying to do numerical integration of my posterior distribution in a two-dimensional problem when we didn't have fancy computer tools available to us, and I knew that the distribution was concentrated on a ridge because these things were highly correlated. So to do my quadrature, I rotated the axes to try and align the larger and smaller axes of the ellipsoidal, roughly, ridge. And just did it. It turns out later that some other people thought, hey, this is a great tool, and published it as a method of doing quadrature in Bayesian tools before we had MCMC. So things like that I've worked on. Matrix variate normal distributions. Again, somebody else wrote a nice paper after I'd used it first and never really thought of it as a generic tool. So these things happen. We do have nice algorithms that come out, and I do want to understand how things work. I do feel that when I'm building a complex model for a particular application, I do worry about how this thing behaves, whether there's some kind of odd quirk going to happen because of the way I bolted together this component of the model and that component. And I did have a little bit of a foray into model checking for complex models, not very successfully. Doesn't answer your question, I'm sure, but I rambled on.
Thanks.
I don't see any hands at the moment, so I might use this opportunity to ask my own questions. Lately in machine learning, there seems to be a real push to solve problems end to end. So you have one model that takes in your data with minimal pre-processing and just spits out the answer. And it seems like the methodology in statistics is quite the opposite. You usually have a lot of steps and they're all sort of well thought out. And I wondered if you could comment on this trend, if you think it's desirable, non-desirable, poor methodology, etc.
If you want your methods to be used, making them simple, coding them up, having a straightforward way as possible of the user using them is obviously an advantage. And again, I've never been good at doing that, being far more interested in just moving on to the next problem. And that's obviously good. Problem with Bayesian methods is it's really hard to do that generally because even though the models for data can be quite generic, the modeling of the prior knowledge underneath it isn't necessarily. And so you don't get very, very widely used Bayesian software packages that are user-friendly. You get things like bugs and its successors that are what you might call user-hostile. But if you know what you're doing, they get the answers for you, but they take work. So it would be nice, it would always be nice if things were very easy for people to use. My problem is that people out there, if they don't know what they're doing, we've got the garbage in, garbage out sort of phenomenon. How can you use a tool if you don't actually understand what it's doing and why it's applicable to your problem? So I'm very wary of snap it, throw the data into this nice package because that's what the other guy next to you in the desk next to you or somebody published in your field did.
So I guess in a sense, the easier it is to use, the easier it is to misuse. And that's always the difficulty. That's
true. That's true. And I don't know, educating people obviously is an important feature here. I mean, I work with people who try to inform decision makers, and decision makers are terribly dumb when it comes to understanding uncertainty and modeling and so on. And I don't know what you can do about it. You present them with these things, and they clearly misunderstand what you've given them. And if you give them any kind of an estimate, they will ignore your expression of uncertainty. So I generally try not to even give them a central estimate. Like say, it's within this range. And they say, well, yeah, what value should I use?
So I think I can agree with that experience. We have a question from Andrew, actually.
Hi, thanks for your talk. You might have already started to answer this, but another contrast between the way that statisticians use Bayesian reasoning, as you've explained in your talk, and also the way that machine learners tend to view it, is that it seems that at least starting with the Bayesian neural network community, maybe in the early 90s, one of the reasonings that people have used for Bayesian inference in machine learning is not that I understand my problem and I have a prior and I want to compute the posterior. It's more that I have a model, it works really well, neural networks, for example, but I have problems that this model is overconfident. Maybe if I just add in some Bayesian flavoring to it without really understanding my prior, it will solve these problems in some measure. But I'm never at a point where I'm like, this is my model, I really believe in it. Do you have a comment on like that kind of idea of like just not really understanding your model, but taking a model that kind of works and saying, I want more uncertainty here, so I'm going to try to make it Bayesian in whatever way I can?
Yeah, it's another thing that I've never been very good at, is sort of saying, oh, this will do, this is an approximation, or this will work. I always want to get down and understand it more deeply and why. I sort of envy people who are just good at making things work without necessarily understanding why, but they're never going to tweak this, or they've got to add something there, and that'll get them the sort of answer they want. And I'd say I envy that, because it's actually clearly a very valuable practical skill, and all I can ever do is to come on afterwards and say, yeah, and that works because this, as I've said before. Yeah, so it's a kind of engineering mentality rather than a physics or science mentality to get on and do things. And I don't decry it at all. In fact, as I say, I envy the ability to do that. But you are going to get some fairly strange chimeras coming out at the end of you've cobbled these things together. And I'd even be a little bit more worried as to whether they actually might interact badly and behave strangely in ways you haven't yet predicted until you throw it out there into the real world. You know, we bring up our children to believe the things we believe, but then they go out into the real world and they're on their own. They still carry your name. That's a real, you know, whatever they do. Anyway, sorry.
Thanks very much.
Great. I'm just looking at the chat here. I see, I think Hensman has, I'm not sure if it's a question or a comment. Did I borrow? Okay. Without hearing anything from him, actually, I see.
Sorry, yeah, that's more of a comment. I guess we were getting into this idea of, you know, reporting a range rather than a point estimate, and you know, most clients that you would work for often demand, you know, what number should I use, as Tony points out, and I have exactly the same experience. And something that Peter Diggle taught me a while ago was never engage with that conversation. And Peter also suggested, don't even report a range. Just say, what is the probability that an event is going to occur? Which sometimes means, you know, choosing what is the probability that the number that you're interested in is going to exceed some threshold. And that sort of puts the burden of choosing the threshold on the client. And I guess in a roundabout way, what I'm doing with that is sort of eliciting from the client, what is the threshold that you're interested in?
Yeah, that's very valuable. Yes, indeed. I would tend to prefer to give them the whole probability distribution and say, there you go, that's it. But people don't understand those things thoroughly. And so it's important to give them relevant and meaningful summaries. And so, for instance, the probability it's less than some threshold is a meaningful summary for them if the threshold is meaningful. So that you've asked exactly the right sort of question there. I'm currently engaged with some people called metrologists. Do you know what metrology is? Most people think it's weather forecasting, but it's not. That's meteorology. Metrologists are people who are, well, they study measurement. Metrology is the science of measurement. And they, since the 1980s, have insisted that measurements should be made with an expression of uncertainty. So they do that, but from way back, it's old frequentist sort of method. So you just get a point estimate and an estimate of the standard error of that estimator. I've been trying to work with these people, bring in more Bayesian methods, and saying you should report a probability distribution for this thing that you're interested in. They call the measurand. You should report the probability distribution for it, which of course you can't do unless you're a Bayesian. So that's a win for a start. But then the client, the person who receives this, who wanted the measurement done, doesn't understand that. You need to give them appropriate summaries, and one such summary is a median value. I wouldn't give a mean, because the median is clearly understandable. It's 50% chance of being above or below, and then you can give them an interval. So simple summaries like that, and just actually submitted a paper on that for the metrology community.
Oh, interesting. I'd love it if you could share a link.
It's not on the bibliography. Yeah, send me an email.
Thanks.
Great. I think Adria has his hand up again.
Yes. If no one else is asking, I may as well ask and pick your brain. So basically, the question I want to ask is, in a broad sense, why are you a Bayesian instead of something else, right? And the angle I'm coming at through this is, it's very attractive to have beliefs that are probabilities, because it gives you a range of tools and things you can do with them. But it's not always easy to figure out what the probabilistic beliefs of people are. And you talked about this with the Shell framework and eliciting experts and stuff. But even when you elicit experts, their estimations of the probabilities are wrong. And even then, eliciting the probability at certain points, you have to interpolate in the middle, right? And why is this the appropriate Bayesian thing to do? And like, basically, how do you deal with the ubiquity of beliefs that are not probabilities?
Right, okay. So why am I a Bayesian? I became a Bayesian the following way. So at University College London, where I did my undergraduate degree, Dennis Lindley arrived as the professor in the latter stages of my course there. And he taught a course on Bayesian decision theory in the final year, which I thought was wonderful. He's a wonderful speaker. He's a very clear presenter, and he has the most he's died, but he had the most amazing way of being able to write on a blackboard in perfect copperplate script. I mean, it was beautiful to watch, but also the ideas were just so right. But I knew that, that this is not how statistics is done. I mean, people don't do it like that. So I went, and I had, between my BSc and my PhD, I spent 2 years in the electricity industry, working for the Central Electricity Generating Board in their statistics group, which was servicing their experimentalists in their various laboratories. I worked mostly with the nuclear labs at Berkeley. And it was actually observing real scientists and how they reacted to the frequentist things I was telling them that persuaded me that everybody really is a Bayesian unless they've been taught otherwise. So that's what made me into a Bayesian. And I went back to UCL to do my PhD with Dennis Lindley, specifically because of that. I used to say, by the way, if somebody came up and showed me a better thing, or why Bayesian methods are wrong, of course I'd go along with it. I don't believe for one moment now that I would. I think my mind is sufficiently closed on these things. I've spent so much of my career arguing with people who disagree with me and telling them why they're wrong. I'm never going to accept anybody else's ideas now. So yeah, that's it. But of course, you're right. You're required to do things to specify probabilities for everything, and you don't know what they are. Or in a sense, you do, because they are your beliefs. They are somehow a property of you, but they're sort of in your head, and you can't open up your head and put some calipers in and measure your probabilities. So we had to acknowledge this from the start. And the very first book I wrote was called Probability: Methods and Measurement. And the essence of this book was to teach people subjective probability ideas. And the premise of it was, where do probabilities come from? If you're taught probability and you take an exam in it, what sort of questions do you get? You get two kinds of questions. One is, given these probabilities, compute some other probability. So given this, this, and this, apply the laws of probability and the theories you know to get the answers to this question. Or, without telling you the probabilities, we'll tell you that a dice is being tossed, or some cards are being, or a fair coin is being tossed. Things where you're supposed to know the probabilities. Well, that's not the real world. Okay, the real world has all sorts of probabilities that are not like that. So this book was about subjective probability, and I introduced the idea that there's a true probability, which is your true real belief. If you were able to be a super person who can assess all your evidence, everything you know, impartially and perfectly, evaluate all of that, compare your probabilities down to the 15th decimal place. This is what super you would give as your probability, and that's the true probability. Anything you try to do to get to that is a measured probability. And I introduced the idea of measurement error in your probabilities. And I said that, how do you improve your probability measurements? You think harder, you do clever things, and in particular, you use the laws of probability. So if somebody asks me, what do you think is the probability if when I toss 10 coins or toss one coin 10 times, I will get 6 or 7 heads? I don't just think to myself, that looks like around a probability about 0.2, 0.3. I apply the binomial theorem, okay? That's what probability theory is for. Probability, every law of probability is simply a tool for me to measure better my probabilities.
Okay, thank you. It's still unsatisfying in that, what's your probability distribution over the errors in your measurement of probabilities? You kind of need to know that to treat the whole thing in a Bayesian way.
Yeah, absolutely. You end up with horrible infinite regress if you try and do that. I never try and do that. The nearest I've got to that is the last thing in my talk, in which we try to express uncertainty about the uncertainties the experts have. But that's still my uncertainty about their uncertainty. I don't ask for my uncertainty about my uncertainty. That's just, that's a no-no. Because it's unprofitable. You have to accept it. You can't measure it.
Yeah. Okay. This, I'm still convinced that there is a theory out there better than Bayesianism that we have not found yet. Because
you may very well be right. And it's almost certainly true in the sense that all theories are wrong. But we need some major Einstein to come along and show us that. Yeah.
Thank you.
I had a question just to follow up on this. So sorry for interrupting the talk. I saw it advertised, and even though I'm not part of CBL anymore, I felt like I had to join. But just picking up on the question of refining your beliefs about probabilities, I thought that was an incredibly helpful comment, actually, because it reminds me of what Andrew Gelman wrote on his blog one time. He sort of was wondering about whether Bayesian inference makes any sense at all. And he argued that this was because Bayesian inference required you to write down your prior distribution based on your internal beliefs. Now, if you could actually do that in an accurate way, then he argued that was the same problem as looking at your data and then writing down your posterior belief immediately as well. So he kind of said, well, what's the point in like going through your prior first and then using the Bayesian machinery to find your posterior? Because, if you can't write down a prior distribution directly from your, or if you could write down a prior distribution directly from everything you've observed so far, then you would also be able to write down your posterior distribution from everything that you've observed so far. But if I understand correctly, your point is that the rules of probability are a tool that allow you to kind of elicit what the implications of your beliefs actually are, which then allow you to go back and modify the assumptions that you can express somehow. Yeah. Did I understand?
Absolutely. Essentially, Bayes' theorem is another theory of probability, which helps you to measure things more accurately. So I call the process elaboration. So if somebody asks you, why do you think that, where did that probability come from? You elaborate, you explain where it came from. And way back in the book, which is many years ago now, I identified Bayes' theorem as one of the most important elaborations, most important theories of probability, because it separates out the two things that combining them in your head in one go is hard. Your other knowledge and the data. So you separate that out. You have one piece of thinking about the data and create a likelihood, another piece of thinking about your prior information, then Bayes' theorem takes over and combines that. And you nearly always you would feel more confident in that as an expression of what you should believe after seeing the data than directly thinking about your beliefs after the data. But there are exceptions. So if the data come up with some surprises that make you think, hey, my model is wrong here, and going back and thinking what your prior beliefs about the parameters of that wrong model would have been, or even thinking about what would have been a better model after you've seen the data, is dangerous. So at this point, after you get these surprises, it may be that your judgment is better made directly without using Bayes' theorem. But at that point, you would always, I think, want to get more data to confirm.
And then you might want to use Bayes' theorem again, possibly.
Yes, yes. Then you might, if it doesn't throw up any new surprises, yes.
Great, thanks very much. Very interesting.
Great. Does anyone else have any questions? Okay, I might quickly barge in with one of my own then. As a more recently converted Bayesian, I get the feeling that Bayesianism, in theory, which is what you've just been talking about, is actually quite different than Bayesianism in practice, where priors are basically just chosen to either be your favorite distributions of normal, uniform, gamma, whatever, or what's analytically, what is easily analytically tractable with your model. Does that bother you ever?
No. So given that all of this is, you know, an approximation, a best approximation in the circumstances, you've always got a finite amount of time. You've always got a finite resource to work with. So super you can't get in there and analyze things to the nth degree. So we always do things that are what we feel is the best approximation, if you like, given the available resource and the circumstances. It's not worth thinking about your prior in too much detail when you've got a reasonable amount of data. You know, so a prior which broadly catches where you think the thing is likely to be and how uncertain you are, it doesn't need to be thought about to any more detail than that, which is why the elicitation generally works quite well. It's going to fail if the application that this distribution is going to be put into is such that the tail shape, for instance, is critical. Okay, because you really cannot elicit the weight of tails because people don't have experience out there. So you know sometimes that you'd rather what you're doing is not a good enough approximation, but still you may have to use that. So I'm very happy being pragmatic, but I want my pragmatic stuff to be such that I can justify to myself that this is in some sense close to what I want. So I have a sense of what the ideal is. The ideal is the full Bayesian analysis, and I want to feel I'm getting close to that in some sense. even though I can't measure that sense.
Okay, makes sense. So if I understood it, your opinion is that practically you can use these crude tools to get close enough to the ideal, and if you have enough data, then everything should be fine.
And also, it's one of these, you know, all applications, all practical things require skill based on experience. You gradually build up with experience learning about these things. So do these things. Do put down a simple prior, but by all means try to. What happens if you use a different one? Does it matter? Does it produce a quite different answer? If it does, then you have to think. Woe betide you if you have to think.
Cool. In case anybody feels a bit shy to ask a question while the session's being recorded, I'm going to end the recording, and then we can have an offline discussion.